For a long time, computer programming languages like Fortran, Pascal, and C were used to describe computer programs. But there isn't any language to describe the digital circuits. This is where hardware description language HDL came into play. There are mainly two types of HDL: Verilog HDL and VHDL. Verilog, a HDL used to model electronic systems, is standardized as IEEE 1364. In 2009, the Verilog standard IEEE 1364/2005 was merged into the system Verilog standard, creating IEEE standard 1800/2009. The current version is IEEE 1800/2023. It was developed by Gateway Design Automation in the mid-1980s and later acquired by Cadence Design Systems. Think of it as a programming language, but instead of writing software to run on a computer, you are describing how hardware circuits should behave and operate. So Verilog is used to describe the behavior, structure, and design of electronic circuits, specifically digital circuits. Simulation. It allows engineers to simulate how a circuit will behave before actually building it in hardware. Then comes the synthesis part. Verilog code can be converted into real hardware using tools to generate gate level implementations. For example, the FPGAs and ASICs. So why to use Verilog? Verilog is for efficient design. It is standardized and scalable. The basic structure of Verilog, it uses modules to define hardware blocks. A module is like a blueprint for a piece of hardware and can include inputs, outputs, and logic. Verilog supports many levels of abstraction: behavioral level, register transfer level, gate level. Now let's make a half adder, which is a basic digital circuit that adds two binary digits, bits, and produces a sum and a carry. Now the truth table of half adder will be something like this. So how are you going to describe a half adder in Verilog? So this is how you are going to write a half adder code in Verilog. Now what is happening in this code? Module declaration. In module declaration, you have module half adder. It defines the name of the circuit block. We have input A and input B, which specifies the two inputs to the circuit. Then we have the outputs, sum and carry. Once this declaration is over, we do the logic implementation. Assign sum equals to A XOR B. It describes the XOR gate logic for calculating the sum. Assign carry equals A and B. It describes the AND gate logic for calculating the carry. And then comes the hardware representation. This code corresponds to a circuit with an XOR gate and an AND gate connected to the inputs A and B. Once this is done, we simulate the half adder. So we can simulate these Verilog code using software like Model Sim, Vivado or Quartus to verify its behavior. A simulation test bench might look like this. We have a module test bench where we declare inputs as registers, we declare outputs as wire, then we instantiate the half adder module like this, and then we test different input combinations. So the expected simulation output is something like this. Now this relates to the truth table we initially discussed of an half adder.